Hi guys, today I would like to start a fresh chapter, electromagnetic induction. So far we covered so much which is related to electricity and magnetism. And the electricity and magnetism, they both are considered in early stages, means they were considered as separately. They both are unrelated phenomena. So that was a long time assumption or long time thinking, long back. But we dealt with Ampere's law and Oersted experiment. So when Ampere's law and Oersted experiment says about that, so we came to know that a current carrying conductor is a source of magnetic field. So current carrying conductor is a source of magnetic field. That the proof shows that if you sprinkle iron filings around a current carrying conductor, the iron filings they will align in such a pattern. So that pattern is due to because the presence of magnetic field. So the alignment of iron filings gives the evidence that existence of the magnetic field. Now here, if you ask a question, what is the source of magnetic field? Magnetic field source. The source of magnetic field is none other than this current carrying conductor. Current carrying wire, simply you can write. So a current carrying wire generates magnetic field. So this was understood by Oersted experiment. Now let us think about converse. What does that converse means? Suppose if I have magnetic field, if with the help of magnetic field, can we produce current? Is it possible? With the help of magnetic field, can we produce current? Can we produce current? So the first tried, or the first person who think this, how a current carrying element generates a magnetic field, like that, if with the help of magnetic field, is it possible to generate current? So that first attempt made by Faraday and Henry, so they came up with certain experiments. Those experiments are very different and very interesting. Let us see those experiments one by one. So we know that a bar magnet, so a bar magnet is a source of magnetic field. And not only that, other than the bar magnet, if a current carrying coil or if a current carrying conductor, so if I take a current carrying wire, so this a current carrying wire produces magnetic field. Here there is no bar magnet. So this current carrying wire or current carrying conductor is a source of magnetic field. So the magnetic field source are the two. One is bar magnet, means natural magnet. Second one is a current carrying coil. Suppose by using these two sources, now the experiment is like this. According to Faraday experiment, a current carrying coil is just connected to a galvanometer. So instead of connecting it here, so it is connected to a galvanometer. Now here galvanometer is not showing any deflection. The reason is that there is no current. Current is not flowing. Current I equal to 0. If you can closely observe here, the dots, so these small tiny dots are representation of electrons. They are stationary. Not only that, this coil is not connected to any voltage source, but here just a voltmeter is connected. But Faraday experiment says, suppose if you move a magnet towards to the current carrying coil, if you move magnet towards to the current carrying coil, so it depends upon the relative motion. Now if you can see, a change in magnetic field is visible clearly behind the screen. How the magnetic field lines patterns are changing. So that magnetic field lines changing throughout this coil. So when we move this bar magnet to and fro or in and out through the coil, you can notice electrons are moving in the coil. If the electrons are moving in the coil, so it means in that case current is existing. Suppose if you can switch the bulb at here to see that effect, if you move a bar magnet in and out through a coil which is connected to a bulb, so this motion causes, here the very important term is motion. If there is no motion, there is no current. But if there is a motion, and that motion also depends or affects the current. Suppose if you move slowly means very slowly. If you can see, the intensity of bulb is less. Suppose if you move fast, the intensity of light is more. So the very important thing is that the motion of the bar magnet. So here the motion causes what? The motion of bar magnet causes change in magnetic field. See how fast you move, that much fast the magnetic field is changing. So the magnetic flux or magnetic field is changing, that causes current flows in the coil. That we can talk, but let us try to observe first at here. So if you move the bar magnet in and out in a coil, so that causes electrons to flow in the coil and that contributes current. So this is the first experiment which is observed by Faraday. Now let us change the setup. So as per I said, bar magnet is a source of magnetic field. Other than the bar magnet, we know that a current carrying coil is also a source of magnetic field. So a coil which is connected to a cell, so current is flowing. So the compass here shows the evidence of the existence of the magnetic field. Okay. Now if I take the setup in this case like this. Now instead of taking a natural magnet, so if I take a current carrying coil, now this current carrying coil is also a source of magnetic field. A current carrying coil equal to source of magnetic field. Now what happens if I move close to this coil? So we see the same effect. So the same thing what we observe at here. So how you move the coil with respect to relative to the another coil. So the motion causes change in the magnetic flux. The change in the magnetic flux induces or cause a current flowing in the another coil. That current cause the reason to glow the bulb. Suppose if you bring this current carrying coil which is very close to the, or you can keep which is inside the another coil. Now if you can call this as a source coil. Now in the source coil the current is flowing. Yeah, current is flowing. But why? The bulb is not glowing at here. The bulb is not glowing at there means in the another coil the current is not flowing. What's the reason? Because there is no change. At this moment there is no change in magnetic flux. There is no change in magnetic flux. So to get the current in the another coil, so this condition is very, very important. Flux should be changed. How the flux should be changed? You can move it. You just move the coil in and out. Or another way also you can do it. Here I am having an option button. So if you can on and off the button like that. So here this causes on and off, the polarity of the cell is changing like this. So this also causes a change in the magnetic flux. So here there is no motion of the coil, but there is a change in the flux. This can be done with the help of a switch or tap key. By connecting tap key, so just keep on press on and off like that. So that causes change in the magnetic flux. So that magnetic flux induces current in the another coil. So this is something is very interesting, and to learn about it. So these are the experiments which shown as an experimental evidence that a change in the magnetic flux causes current at here. So these experiments are performed by Henry and Faraday. Suppose you know that this cell is a DC source. DC source. Here I am having an option. That option, if I can switch to AC source, means the source known as alternating current. We will talk in detail that about in later. So that is also one of the source of current. And if you can pass alternating current right now in first coil, or you can take this coil 1, alternate current we have given. So alternate current having frequency and magnitude and all. Okay, for a moment no need to know about that. So now alternating current. The current which comes to our house, the current right now what you are using other than the DC sources, that is known as alternating source. Now that alternating source, if you connect to a current carrying coil, that obviously causes a change in the direction of current in the coil first. That causes a change in the magnetic field lines. Now here there is no mechanical motion, there is no mechanical operation of switch. We can talk about this later in detail, but let me stick with this one. So if you change, if you do like this action, it is a very fun, very interesting to do. I enjoy to do like this. So the change in the magnetic flux causes current in the another coil. So by using these all experimental evidence, so we can conclude a current can be generated by using magnetic field. Yeah, here's some action we need to do. So that is a mechanical action, but what the reverse? So here, if you can take for a moment, now I am having a setup. So this is a bulb which is connected to a coil, and for a moment, so this bar magnet is connected to a wheel. So that wheel can be rotated with the help of flow of water. Or this is an example of production of electricity, hydropower. So water rotates turbine fixes magnet. So when magnet rotates, obviously it's changing magnetic field nearby. Now in the nearby, if we can keep a current carrying coil or a coil, now the change in magnetic field causes current in the coil. So in this coil current is coming. So current is due to because of at here change in magnetic flux. Change in magnetic flux. So these are the experimental evidence that. So this experimental evidence shows that how magnetic field is generated by using a current carrying coil. Like that, the converse, the reverse is also possible. So but in this reverse case, a change in the magnetic flux induces current. Now let us talk about magnetic flux. I already discussed about magnetic flux. Just recall what is magnetic flux. Magnetic flux and electric flux, they both are having same. Let's think about that first. How we define magnetic flux? So we can define flux as the number of magnetic field lines crossing per unit area. So that is the standard flux definition. The number of field lines, either the electric field or magnetic field. The number of field lines crossing per unit area or a given area is defined as flux. So if I show in a diagram, suppose I am having magnetic field lines, that is the direction of magnetic field lines along the east direction. So if the magnetic field lines are passing along in this direction, let me take one more. Yeah. Now in this magnetic field, if I consider an area, suppose I have taken an area. So let me take this area like this. Now, so through this area, how many magnetic field lines are passing? Through this area, how many magnetic field lines are passing? So here clearly you can see the area is covered totally. Now the number of magnetic field lines are passing in this case we can count easily because the field lines are drawn such a way like that. How many field lines are passing at here? The magnetic field lines are passing just 5. So as a definition we can say that flux phi equal to the magnetic flux pi equal to normal component of magnetic field B cross surface area. So what is the meaning of normal component? Suppose if I am having x and y axis, so if this is magnetic field line, so this magnetic field line is making an angle with the components. So if it makes this component as theta, so this we can call B cos theta and this we can call B sin theta. Now the B cos theta component, we take that as normal component. Now we can define flux pi equal to, so B dot A, we know that formula, flux pi equal to B bar dot A bar. So in vector notation that we can write that. So the dot product of two vectors flux pi equal to BA cos theta. So here theta is the angle between area vector and magnetic field vector. So they both are vectors. Now let us think about a case. Suppose if I have area along in this direction. So let's imagine that. So this is the area. So now if I draw the area vector, so the area vector is perpendicular. So the area vector is always perpendicular like this. Now in this case, if I highlight the area, so this is the area. Now if I draw the magnetic field lines, so the magnetic field lines, I will draw one more. I don't draw everything. So these are the magnetic field lines. Now what is the angle between area vector? So this is the area vector and this is the magnetic field vector. So in this case, the angle between them goes to theta equal to 90 degree. So if theta equal to 90 degrees, what is the flux value? Flux pi equal to B dot A cos theta. So here theta equal to 90 degree. So flux pi equal to BA times cos 90 degree. So we know that what is the cos 90 degree value. So by that case, flux equal to 0. So that is literally the number of magnetic field lines are not crossing anything at here. Now if I change the area, suppose this time if I draw the magnetic field lines, so this is the magnetic field lines. So let me draw two more. So the magnetic field lines are the going eastward direction. Now if I consider an area, now in this case the area is representing like this. Oops, yeah, let us understand. So if this is area and the area vector, now I draw the area vector. The black color is area vector. This is area vector. Now the area vector making an angle with the magnetic field equal to 0. So here they both are parallel, theta equal to 0 degree. If theta equal to 0, what is the flux value? Flux pi equal to BA times cos 0 degree. Cos 0 value equal to 1. So by the time the flux, in this case, flux pi equal to BA, which is positive. So let me take one more case. What happens if I flip this in the above case, if I change the area vector direction? Suppose this is magnetic field lines. Magnetic field lines, let me draw one more. Suppose if I take a surface area, so this time I would like to take the circle. Any area you can take, there is no problem. So if this is the surface which I consider in the magnetic field, but now this surface is showing area along in this direction for a moment. Now magnetic field direction and the area direction at here is exactly opposite. It means the angle between them. So here the angle between them goes to how much it is? Theta equal to 180 degree. So in this case, flux pi equal to BA times cos 180 degree. Cos 180 value equal to -1. Therefore, flux equal to minus B times A. So by the conclusion, I can say that flux is positive and flux is negative and flux is equal to 0. This all depends upon the theta. So theta is the angle between magnetic field and area vector what we consider in the magnetic field. So after defining flux, remember this flux formula, same, flux pi equal to simple vector notation B bar dot A bar. Okay, so if you can write its SI unit. So SI unit we can write in terms of SI unit of magnetic flux is Weber. Weber we can represent that as WB. So we can define as 1 Weber. Suppose if you write this as 1 Weber, 1 Weber is the flux produced when a uniform magnetic field of 1 Tesla normally over an area of 1 meter square. So if I can call this flux as 1 Weber, so this 1 Weber will give if 1 Tesla of magnetic field, magnetic field units are Teslas. If 1 Tesla of magnetic field crossing an area of 1 meter square, area units are meter square. 1 Tesla of magnetic field is crossing 1 meter square area that we define as 1 Weber. So we can write that 1 Weber as 1 Weber equal to Tesla meter square. So 1 Weber equal to 1 Tesla meter square. So I can say that Tesla meter square are the units of flux. So when it comes to CGS units, we are having CGS units also. So CGS units we can call as Webers in terms of Maxwell. In CGS units, the flux SI unit is Maxwell. We know that the magnetic field in the CGS units are nothing but Gauss. So meters in CGS units goes to centimeter square. So I will give a relation. That relation gives that 1 Weber equal to 10 power 8 Maxwell. So this is the relation between SI unit to CGS units. So finally, I can conclude by giving an important point is that, so Faraday's experiment shows that a change in magnetic field can produces current. Now to find that change in magnetic field, we define about that magnetic flux. So the flux formula comes flux pi equal to B dot A, which equal to BA cos theta, and flux is positive and flux is negative and flux is 0. So we define a flux as the number of field lines, here magnetic field lines crossing per unit area that we define as flux.